Hello, welcome to another video. Today we're going to be focusing on the Fundamental Theorem of Calculus and applying this to an AP style problem. So here we've got a fairly old FRQ. I encourage you guys to pause the video and read this entire problem yourself. We are just going to get started with solving it. So here we've got a function and we want to compute some values. So this right here is sort of your classic accumulation function where you will start at x equals 1 and then you integrate this. Well, I guess we can label this t, this is f of t, and we're going to integrate until some certain endpoint, x. I'll sort of put that over here, and this is x. So just to sort of get an intuitive feel for this function, when x is exactly 1, you've got no area to integrate, so the function would just be 0. And then as you continue along here, you can see that if x is greater than 1, we're going to be sort of integrating forward in the forward direction. And so we're going to continue increasing because f of t is above the t-axis, and then we're going to decrease for a little bit. But the main thing that might be a little bit confusing is as we go backwards, we're going to get more negative because even though this area is positive, we're going backwards, so we have to put a minus sign. And we'll see this more concretely when we do mathematically calculate this. So first let's start with g of 4. So g of 4 would put our x over here, and so we want to figure out what this orange area is, and of course this small triangle too. So we split this up into some composite shapes to make this easier to work with, and at this point we can just add up all these areas. So let's find g of 4. We know that that's from 1 to 4 f of t dt, and now we're just going to add up the areas here, and I'm going to sort of draw the shapes to help visualize. So this right here, that area is this sort of triangle right here. I'll sort of represent it. And what are the dimensions of this triangle? Well, you know that this, from the graph, you can see it's 3, right? From 1 to 4, that's 3 units. And then that will be 1. So we've got a 3 by 1 triangle. And now we're going to add another one, which is right here. That's going to be a square, and that's a 1 by 1 square, right? Because this length is 1. And note that this sum is actually a integral. This is a sort of from 1 to 2 f of t dt, and we're going to add on more so that we can go all the way to 4 instead of just ending at 2. So now we're going to consider this orange region, which is from 2 to 3. So this right here will be from 2 to 3 f of t dt, and we're going to have just a 1 by 1 sort of triangle shape that'll look like this, right? Because you can see from this diagram that the height will be 1, and the width is also 1 because we're going from x equals 2 to x equals 3. And finally, we're going to subtract this green region right over here, and it'll sort of be sort of the same dimensions, right? A 1 by 1 triangle, and this is going to be from 3 to 4 f of t dt. So when you add all of these up, the integral properties, from integral properties, you know that you will end up getting the full 1 to 4 once you add up all of these areas. We've got these two. So these two, notice how these two are essentially the same triangle, right? So you've got that triangle on the minus exactly that same area. So without even calculating the area, we know that that just goes away to 0. So we're left with these two. So now this becomes 3 times 1 over 2, and then we're adding 1 times 1, which is just 1. We usually don't even bother writing the 1 here. And so now the 1, we can replace that with 2 over 2, and so that becomes 5 over 2. So that is the value of g of 4. Great. So now we find g of minus 2. And so we go through a similar process, right? So start with 1, and we're going to end at minus 2. This is our x. But recall that we're going backwards, and so our answer should be negative, because we've got a positive area, but then we switch it around. So we've got over here g of minus 2, so that's going to be from 1 to minus 2 f of t dt. Now this we're sort of integrating backwards, and from integral properties you can just switch the bounds and then place a minus sign, so you get this new integral. So this is what I meant by integrating backwards has a opposite sign, right? So then keeping that minus 1 in check, and now we've just got to deal with this integral where we can now sort of integrate forward. So we know that this length right here is going to be 1, 2, 3 units, and that one will be 4. So this whole area is going to be 12 divided by 2, or 6. So we got minus 1 times a 6, so we just get minus 6. So that is a value of g of minus 2. Great. So we've solved part A. Now let's move to part B, where we are finding the instantaneous rate of change. So this is g prime at x equals 1, so g prime of 1. So let's write g of x again. Get 1 to x, f of t dt, and now if we just take the derivative of both sides, we know from the fundamental theorem of calculus that g prime of x will be equal to f of x. And this one doesn't really matter, because it doesn't matter where you start, it's just how g is changing, right? So now all we have to do is plug in 1 here. So g prime of 1 is f of 1, and from the graph we can see that f of 1 is 4. So that is going to be our value of g of 1. Now we move to part C, where we're finding the absolute minimum value of g. So the first thing that we can do is we know that we're looking for critical points of g, right? So we know that g prime is f, right? And so that means that when we draw a sign chart for g prime rather, it's the same thing as f. And so f crosses the x-axis in only 2 places, right? At minus 2 and 3. So we draw those here, so minus 2 and 3. And then we've also got to include the endpoint on our sign chart, which is 4. And now we know that g prime is positive from minus 2 to 3 because f is above the t-axis, right? Over here. But then it's below the t-axis, f is negative over here. So we put a minus from 3 to 4. So now we're looking for an absolute minimum. So this can happen either at critical points or at endpoints, right? But here, the only critical point is 3, x equals 3. However, x equals 3, we can see g prime changes from positive to negative. So that means x equals 3 is a relative maximum, right? So to draw this, you can see that the value of g at x equals 3 is higher than its immediate neighbors. So that means that automatically disqualifies it from ever being an absolute minimum, right? You're higher than your neighbors. How could you be lower than everybody else? It doesn't make sense. So that means that all of our critical points, or all 1 of our critical points, cannot be an absolute minimum. So all we have to do is just look at the endpoints, which are x equals minus 2 and x equals 4. So it's probably no coincidence that we've already found the value of g of 2, which was minus 6. So now we just have to worry about g of 4, as we calculated it in the previous problem, is 5 over 2. So here we can see that minus 6 is the lowest of these, and so minus 6 is our absolute minimum value of g on this interval. So in part D, we're looking at inflection points of g. So which ones of x equals 1 and x equals 2 are inflection points? Well, we know once again that g prime of x equals f of x. So once we differentiate both sides, we can see that g prime will actually just be f prime. So now we just have to check whether the sign of f prime changes, right? Because if the sign of f prime changes, then we know that also tells us that the sign of g double prime changes. And that leads us back to the definition of the inflection point, right? That the second derivative, g double prime, is changing sign. Now, one way that we can see from the graph whether f prime changes is to see the slope of the tangent line, right? So that's what we're going to do here. So immediately before x equals 1, we can see that f prime will be positive because the tangent line is positive there. And then right after 1, f prime is negative. So yes, clearly we've got a sign change of f prime because it goes from positive to negative. But what about x equals 2? Well, we can see that f prime is still negative because it's the same tangent line. And then right after 2, we see that it's still negative. So we do not have an inflection point at x equals 2 because f prime didn't change sign. So we know that g prime didn't change sign either. So that means that only x equals 1 is an inflection point for this graph, for the graph of g, and not x equals 2 because the sign of g double prime didn't change. That'll be it for this video. I hope this was helpful, and I'll see you guys in the next one.